Let's talk about a paper. A research paper from 2012 written by just 3 researchers. Now, this paper didn't just win some competition, it basically lit the fuse on the modern AI explosion that we're all living through right now. It was the moment we proved that a machine could actually learn to see, not just process pixels, but genuinely recognize things in the messy, chaotic real world. So today, we're going to break down the paper that taught computers how to see, and in doing so, changed everything. So you gotta ask, right? How did we get here? How did we go from computers being totally blind to the AI in your phone that can spot a cat, a car, or a coffee cup in a photo in less than a second? Well, it wasn't just about writing better code. It was a complete shift in how machines learn. And this breakthrough? It was forged in the fires of a massive online competition, one that used a gigantic library of images to challenge the best minds on the planet. So for this explainer, here's our game plan. First, we'll set the scene, what the race looked like before 2012, and why this was such an impossible challenge. Then we'll dive deep into the AlexNet breakthrough, piece by piece. We'll relive the shocking result that pretty much left the entire field stunned. And finally, we'll look at the world this paper helped create. Okay, so to really appreciate what a huge leap this was, you have to understand the mountain that everyone was trying to climb. Before 2012, getting a computer to reliably recognize objects in just normal, everyday photos was seen as one of the hardest, maybe even impossible problems in all of AI. And this is exactly why it's so tough. I mean, for you and me, seeing is just second nature. But for a computer, a dog isn't just a dog. It's a nearly infinite stream of different pixel data. Think about it, a golden retriever in the bright sun, a poodle hiding behind a couch, a bulldog from a weird angle. To a machine, those are all completely different problems. This incredible amount of variation was the brick wall that computer vision research had been running into for decades. So, to make any real progress, the field needed a common battleground, a standardized test that everyone could compete on, and that test was called ImageNet. Just try to picture a digital library with over 15 million photos, all tagged by humans. The yearly competition used a slice of this, about 1.2 million images spread across 1,000 different categories, from leopards to motor scooters to cherries. The challenge was simple. Build an algorithm that can look at a new photo and tell you what's inside. Simple, but not easy. And as you can see, the best methods back then were just plain stuck. We're talking about really complex, clever systems, but even the best of the best had a top 5 error rate of more than 25%. What that means is, for 1 out of every 4 images, the right answer wasn't even in the computer's top 5 guesses. Progress was happening at a snail's pace, and frankly, a lot of people thought a real breakthrough was still decades away. And then, 3 researchers, Krizhevsky, Sutskever, and Sutskever Hinton, showed up. They didn't just try to nudge the needle forward a little bit. Nope. They brought a whole new kind of weapon to the fight, a huge, deep, convolutional neural network. It was an approach that many people in the field had already written off as way too computationally expensive, way too hard to train, and just not practical for a problem this massive. So their success wasn't because of one single magic bullet. It was this brilliant combination of 3 key ideas. First, they found the raw horsepower they needed in a really unexpected place. Second, they used a way faster, simpler kind of artificial neuron. And third, they invented a clever trick to force their network to learn better. Let's break each of those down. All right, their first secret weapon was pure hardware genius. They figured out that the specialized computer chips designed for making video games look awesome, graphics processing units or GPUs, were accidentally the perfect tool for training neural networks. See, GPUs are built to do thousands of simple math problems all at the same time, which is exactly what a neural net needs. Their model had 60 million different knobs to tune. Training it took 5 to 6 days straight, running on 2 high-end gaming GPUs. Without that insight, they never could have even run the experiment. Next up, the neuron itself. For a long time, networks used what you could call saturating neurons. Think of it like a volume knob that gets really hard to turn once you get close to 0 or 10. It meant that the learning process could slow down to a crawl. The AlexNet team swapped that out for a new kind of neuron that just didn't have that problem. And this little guy is called a rectified linear unit, or ReLU. And the idea is shockingly simple. If the input is negative, the output is 0. If it's positive, the output is just the input. That's it. But this tiny change had a massive effect. The paper showed that their network trained several times faster with ReLUs. That speed boost wasn't just a nice little bonus. It's what made training a network this deep and complex even possible. Okay, finally, they had to deal with a classic AI problem, overfitting. How do you stop a giant network with 60 million parameters from basically just memorizing the answers to the test instead of learning the concepts? Their solution was this brilliant technique called dropout. Imagine you've got a team of experts working on a problem. With dropout, for every single attempt, you just randomly tell half the team to sit this one out. It forces every expert to get smarter and more capable on their own, instead of just relying on their buddies. It makes the whole network much more robust. So they had the hardware, they had the fast neurons, and they had the smart training method. They bundled it all up into a model that we now call AlexNet and entered it into the 2012 ImageNet competition. And when the results were announced, well, let's just say the entire field of computer science got a major wake-up call. The winning number was 15.3%. Just let that number hang in the air for a second. That was their top 5 error rate. And remember, the very best systems before this were struggling to get under 26%. This right here is what a paradigm shift looks like in a bar chart. The runner-up that year, using all the traditional methods, got an error rate of 26.2%, which, by the way, was still considered great. AlexNet didn't just win. It wasn't even close. They beat the next best thing by a stunning 10 percentage points. It was an absolute demolition, and the message was crystal clear. Deep learning wasn't just another small improvement, it was the future. Honestly, you can pretty much divide the history of modern AI into 2 distinct eras, BA and AA, before AlexNet and after AlexNet. The paper's impact was immediate, and it basically set the entire research agenda for AI for the next decade, and you could argue, even to this day. So the single most important lesson from AlexNet was that depth is king. The network was built in layers, right? It had 5 of these special convolutional layers that are great at finding features, and then a few more layers to make the final call. And what the authors proved was that this depth was absolutely essential. If they took out even one of those 5 main layers, the performance got way worse. It wasn't just about having a big network, it was about having a deep one, where each layer could build on what the layer before it had figured out. So, how does a network like this actually see? Well, it's not memorizing photos of cats. It's learning a hierarchy of ideas. The very first layers, they learn super simple stuff, like how to spot an edge or a patch of color or a texture. The next layer up takes those simple patterns and learns to combine them into slightly more complex shapes, like an eye or a nose or a car tire. Go deeper still, and those layers learn how to assemble those parts into bigger things, like a dog's face or the front of a car. By the very end, it has built a compact representation, a feature vector that captures the meaning of the image, not just the pixels. What's amazing is that even in their big moment of victory, the authors were incredibly humble. They put this quote right there in the paper's conclusion. They knew that even with this incredible breakthrough, they were still just at the very beginning of a long, long road to creating a machine that could see and understand the world like a person can. And really, that's the ultimate legacy of this paper. AlexNet proved, beyond a shadow of a doubt, that if you have enough data, enough computing power, and the right kind of deep architecture, you can teach a machine to perceive the world. It kicked open the door for everything from self-driving cars to AI that can help doctors spot diseases. But it also left us with the next grand challenge. Because it's one thing to recognize an object in a picture, it's a whole other thing to understand the context, the relationships, the story behind that picture. And that is the next great mountain that the world of AI is trying to climb today.